Prepare yourselves for a grandiose disturbance of remarkable extents. Betelgeuse, the red monster star balanced on the edge of our world, is conveying dismal messages through the universe. Utilizing the James Webb Space Telescope, cosmologists have revealed something significantly disruptive about this titanic heavenly body. As prestigious astrophysicist Brian Cox gives a grave cautioning, the inquiry looms. Are we on the slope of seeing a devastating cosmic explosion blast that could forever change the night sky as we know it? We should dive in. In the grand tapestry of the universe, where stars are conceived, live, and die in stupendous fashion, one star has recently captured the imagination and concern of astronomers and the public alike. This star is Betelgeuse, a red supergiant of massive extents and age, prominently situated in the constellation Orion. Its distinctive rosy hue and variable brightness have long been a source of interest, but recent developments have heightened this intrigue. As we explore the nature of Betelgeuse, we find ourselves on the cusp of a potentially great event in the life cycle of this star. What could these changes in Betelgeuse mean? Are we witnessing the prelude to a cosmic display of unbelievable scale? Betelgeuse, roughly multiple times larger than our Sun, is a stellar behemoth. Its enormous size is almost beyond human understanding. Imagine a star so vast that if it replaced our Sun, its surface would extend beyond the orbit of Mars, enveloping Mercury, Venus, Earth, and Mars in its celestial embrace. This incredible size is not just a testament to Betelgeuse's physical attributes, but also signifies its stage in the stellar life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, a phase characterized by expansion and cooling following a life spent fusing hydrogen into helium in its core. But what about the age of Betelgeuse? This star, believed to be around 8.8 to 8.5 million years old, is relatively young in human terms but ancient in the context of stellar lifetimes. Its current red supergiant stage marks the end of millions of years of stellar evolution, a period marked by dramatic changes and cycles that transformed it from a hot blue star to the red giant we see today. The life cycle of stars like Betelgeuse is a story of transformation driven by the relentless forces of nuclear fusion and gravity. Betelgeuse's distinctive rosy tint is another indicator of its current stage. The red color results from its relatively cooler surface temperature compared to stars like our Sun. While the Sun's surface temperature is around 5,500 Kelvin, Betelgeuse's cooler surface registers temperatures around 3,500 Kelvin. This cooler temperature allows Betelgeuse to emit light at frequencies that give it a red appearance. Yet, this color is not just a visual trait. It provides clues about the star's physical state and the processes occurring within its massive gaseous expanse. Adding to Betelgeuse's mystique is its historical color change. Ancient Roman and Chinese records suggest that around 2,000 years ago, Betelgeuse was yellow. It was only in the 9th century that Arabic scholars first described it as red. This color shift over human history is not just a detail in the annals of astronomy but a clue to the star's evolutionary path. The variable brightness of Betelgeuse is another intriguing aspect. It's a semi-regular variable star, meaning its light periodically waxes and wanes. This variability is a characteristic dance of radiance that has fascinated astronomers and sky watchers for centuries. Typically, Betelgeuse undergoes a 400-day cycle along with a longer cycle that spans around 5 years. These cycles have been documented as far back as 1836 by Sir John Herschel and possibly even earlier in indigenous oral traditions. However, what makes Betelgeuse truly enigmatic is not just its changing brightness but its inconsistency. Unlike many stars that follow a predictable pattern, Betelgeuse occasionally deviates from its rhythmic dimming and brightening, hinting at complex and less understood processes occurring within its enormous structure. A recent historic discovery surrounding Betelgeuse captured the attention of cosmologists and astronomers worldwide with a sudden and dramatic change in its appearance, an event now widely known as the Great Dimming. In late 2019, the red supergiant Betelgeuse, one of the brightest stars in the night sky and a prominent feature of the Orion constellation, began to dim unusually. The star's dimming was so pronounced that it started losing its glow at an average rate of 0.01 magnitudes per day, reaching its lowest brightness in February 2020. Normally visible to the naked eye even in light-polluted areas, Betelgeuse became extraordinarily fainter, a change noticeable even to amateur observers. However, there's one issue with trying to monitor the activities of Betelgeuse: the time paradox. When we look at a star like Betelgeuse, we are not seeing it as it exists in the present but as it was in the past due to the time it takes for light to travel to us. In Betelgeuse's case, at approximately 725 light-years away, the light we see today left the star nearly 7 centuries ago. This delay makes it challenging to predict and monitor sudden changes in a star's behavior, as we are essentially looking into its past. The dimming event served as a reminder of the inherent difficulties in continuous astronomical observations and the limitations of our understanding when dealing with the vast cosmic scales and the time mystery they present. The unfolding of Betelgeuse's stellar drama was closely monitored by Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team. They used Hubble to analyze the behemoth star as part of a 3-year study to monitor variations in Betelgeuse's outer atmosphere. These observations provided unprecedented insight into the dynamics of a variable star like Betelgeuse, which regularly expands and contracts, causing fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed the researchers to probe the layers above the star's surface, which were heated somewhat by the star's turbulent convection cells. Further analysis of the Hubble spectra taken at different points throughout 2019 and 2020 helped in measuring the movement of material in Betelgeuse's outer environment. In particular, the spectra focused on magnesium-2 lines, which are indicative of the star's atmospheric conditions. These observations showed material moving at speeds of around 200,000 miles per hour from the star's surface into its outer atmosphere. This hot, dense material eventually extended millions of miles from Betelgeuse and was the precursor to the dust cloud that led to the star's dimming. Dupree and her team estimated that about twice the normal amount of material from Betelgeuse's southern hemisphere was lost over the 3 months of the event. This mass loss was significant, especially considering that Betelgeuse, like all stars, continually loses mass, though at a rate far greater than that of our Sun. The scale of this mass ejection and the subsequent dimming sparked discussions among astronomers about whether this event could be a precursor to a supernova explosion. The proximity of Betelgeuse, around 725 light-years from Earth, adds to the interest, as any such explosion would be visible from Earth and provide a fascinating opportunity to observe a supernova up close. But the question remains: what does this dimming event portend for Betelgeuse's future? Is it a sign of an impending supernova or just an extraordinary episode in the star's long and complex life? Several theories have been proposed to explain this sudden change. One prevalent theory suggests a hiccup in the supernova explosion process, a hypothesis that gained traction due to the common belief that Betelgeuse is nearing the end of its life. Another popular theory involved dust, possibly from the star itself, obscuring our view. Betelgeuse, like other red supergiants, is known to shed material, and it was thought that this material could form a dust cloud thick enough to dim the star's light from our perspective. A third explanation considered changes in the star's photosphere, the visible surface layer, which could affect its apparent brightness. In-depth analysis using various observational techniques helped unravel this mystery. Spectroscopic studies showed a drop in Betelgeuse's effective temperature, suggesting the dimming could be due to a large dark spot on the star's surface. This theory was supported by the observation that Betelgeuse's temperature dropped by at least 170 Kelvin around the time of the dimming, pointing to significant changes on its surface. Ultimately, the key to understanding this mysterious phenomenon came from humanity's sentinel in space, the Hubble Space Telescope. Hubble's observations revealed that the dimming of Betelgeuse was likely caused by a massive ejection of hot material into space. This material formed a dust cloud that darkened part of the star's surface, effectively reducing the amount of light reaching us from Betelgeuse. The dust cloud was believed to have formed from extremely hot plasma that erupted from a large convection cell on the star's surface and then traveled through its hot atmosphere to the cooler outer layers. As it cooled, it formed dust grains, creating a cloud that blocked light from about a quarter of the star's surface. Hubble's ultraviolet light spectroscopic observations, which began in January 2019, were crucial in piecing together the timeline leading up to Betelgeuse's dimming. These observations captured signs of dense, heated material moving through the star's atmosphere in the months preceding the dimming. In December 2019, Several ground-based telescopes also observed the star dimming in brightness, particularly in its southern hemisphere. This material, which was initially more luminous than the star's usual brightness, eventually led to the formation of a foreboding shadow as it moved. The mass released was significant, measuring several times as much as our moon.